Imagine interacting with generated video in real time, like controlling virtual characters, almost like puppets, exploring these dynamic worlds that just keep unfolding, or stepping into simulations you can actually manipulate on the fly.
Yeah.
Yeah, it's a really exciting vision.
It is, but the reality is, even our best video generation models today, they're often just too slow, right? Too computationally heavy to give you that instant interactive feel.
Exactly. And that lag, that limitation, that's precisely what this paper we're diving into tackles. It's called Autoregressive Adversarial Post-Training for Real-Time Interactive Video Generation, or AEPT for short.
Yeah, and their core point is pretty clear, that these big, powerful video models, diffusion models especially, they give you amazing quality, but they rely on this iterative process. And that process is just too slow, too heavy for the kind of low latency you absolutely need for real interaction.
Okay, so the mission here was to take these pre-trained latent video diffusion models, which are great for quality, and kind of transform them into something, well, fundamentally different.
Right. Something that's not just high quality, but also incredibly fast, something autoregressive so it can handle long sequences frame by frame, and specifically designed for interaction.
And how do they pull that off? What are the key ingredients?
Well, there are a few big ideas. One is generating just one latent frame at a time in a single shot. They call it one NFV, one neural function evaluation. Super fast.
Okay, one step per frame.
Exactly. And they cleverly borrow ideas from language models, like using a KV cache for efficiency, but apply it to generating video frames sequentially. And crucially, they introduce this new adversarial post-training technique using something called student forcing.
Student forcing. Okay, we'll need to unpack that. Sounds important.
Oh, it's key. Especially for tackling error accumulation over long videos.
And the results, you mentioned performance.
The results are pretty striking. We're talking real-time, 24 frames per second at a decent 736x416 resolution, running on just one H100 GPU.
Wow, okay, on one chip.
Yeah, and they demonstrate generating videos up to a minute long, that's 1,440 frames with super low latency, around 0.16 seconds.
0.16 seconds. That's fast enough to feel responsive.
Absolutely. Compared to previous methods, it's a massive leap forward if you're thinking about that interactive potential.
Okay, let's dig into this more then. You mentioned those applications, interactive game engines, world simulators, virtual humans. They sound almost like science fiction. Why is getting that real-time interactive video generation such a tough nut to crack technically?
Well, those applications are ambitious, right? They really push generative AI towards being this live, responsive medium. But the fundamental bottleneck, like we touched on, is how most of these powerful models, especially diffusion models, work.
The iterative denoising thing.
Exactly. They get amazing visual results, but they refine the image or the frame over multiple steps, multiple calculations per single output frame. And that process is just inherently slow and computationally hungry.
Yeah, you can't wait seconds, let alone minutes, for the next frame if you're trying to, I don't know, dodge something in a game or have a fluid conversation with an avatar.
Precisely. Low latency and high throughput, they're just non-negotiable for interaction. And it's not like people haven't been trying to speed things up.
Right. What were the previous approaches?
Well, you had earlier frame-by-frame prediction methods, but they were often kind of inefficient, lots of redundant computation. Then came things like diffusion forcing, which tried to parallelize steps. Better, but still usually needed multiple passes.
Still not quite fast enough for real time.
Generally, no. And then you have models inspired by LLMs using tokens for video, which allows for that efficient KV caching. But they generate token by token, which can make the final frame output relatively slow, even if the individual token steps are fast.
Okay, so this paper saw these gaps and aimed squarely at three things that haven't really been solved together before.
That's right. They identified these three core challenges. One, getting real-time throughput and enough frames per second. Two, achieving super low latency for that immediate user feedback. And three, enabling causal generation that can run for extended periods, like minutes, not just seconds.
Which brings us back to AAPT.
Yeah.
Autoregressive Adversarial Post-Training. Let's break that down.
Okay. So the starting point is a pre-trained latent video diffusion model. They used an 8 billion parameter model called a diffusion transformer, or DIT.
A DIT, like a standard transformer, but trained for diffusion tasks.
Sort of, yeah. It operates within the diffusion framework, and crucially, it works in the latent space. A VAE, a variational autoencoder, compresses the video frames first, both spatially, the image itself, and temporally, across frames.
So they're already working in a compressed, more manageable space. That helps efficiency from the get-go.
Definitely. But the big trick is how they transform this diffusion model, which normally isn't built for single-step sequential generation, into something that is.
Right. How do they rewire it?
Architecturally, they make some key changes. Figure 1 in the paper shows this visually. First, they ditch the standard bidirectional attention you see in many transformers,
Where the model can see both past and future context.
Exactly. They replace it with block causal attention. Causal means it can only look backwards at previous frames. Essential for autoregressive generation, where you predict the next frame based only on what came before.
Makes sense. Can't predict the future by peeking at it.
Precisely. Then they change the model's inputs. After the very first frame, which might come from the user, for every subsequent frame, they feed the actual generated frame from the previous step back into the model. It's concatenated, like an extra input channel.
Okay, feeding its own output back in.
Yes, alongside the text prompt, noise, etc. And then they leverage that KV cache and input recycling, much like LLMs do for fast text generation. So at each step, it reuses the stored computations from past frames and does just one forward pass to predict the very next latent frame. That's the 1NFE magic.
Okay, that 1NFE, one neural function evaluation sounds key for speed. Now, you mentioned comparisons like in Figure 2 to diffusion forcing. How is APT more efficient than even a one-step diffusion forcing approach?
That's a good point, and Figure 2 helps illustrate it. Even a single-step diffusion forcing method, when using KV caching, often ends up needing computation that involves aspects of 2 frames per step, maybe the current noisy input, and some prediction target.
Okay, still a bit more complex per step.
Right. AEPT, because it's designed from the ground up as a purely autoregressive next frame predictor in that single step, simplifies the computation. It effectively just needs to process the past generated frame plus context from the cache to produce the next one. It's a more streamlined path, specifically optimized for this real-time sequential generation.
Got it. Less work per frame equals more frames per second. But what about generating long videos? You mentioned that KV cache. Doesn't it just keep growing and growing with every new frame once you run out of memory eventually?
Absolutely. That's a classic problem for long sequence autoregressive models. Their solution is a sliding window attention mechanism.
Okay, like it only looks back a certain distance.
Exactly. Within the transformer layers, the visual tokens only attend to a fixed number, n, of the most recent past latent frames. In their setup, n was 30 latent frames.
And how much actual video time is that?
Since their VAE compresses time by 4x, 30 latent frames is about 120 actual video frames. At 24 FPS, that's roughly 5 seconds of history it's directly looking at. This keeps the KV cache size bounded.
Early 5 seconds. Is that enough context?
Well, it's a trade-off. But crucially, the attention mechanism always attends to the text prompt tokens and the very first frame of the video. That first frame helps anchor the scene in style. Plus, because you have multiple layers stacked in the transformer, the effector receptive field, how far back information can theoretically influence the output, is actually larger than just that 5-second window at any single layer.
Ah, okay. Information propagates upwards through the layers.
Precisely. It's a way to manage memory while still giving the model a reasonable temporal view.
Okay, so the architecture's tweaked for causality and speed. Uses the KV cache smartly with a sliding window. But you can't just flick a switch on a pre-trained diffusion model and expect it to work this way perfectly, especially for long, coherent videos. This needs special training, right? You mentioned 3 stages.
Exactly right. The training pipeline is absolutely critical. It's a sequential 3-stage process. Stage 1 is diffusion adaptation.
Adapting the original model.
Yep. They take the pre-trained diffusion model weights and basically fine-tune them. The goal is still related to diffusion, predicting a clean frame from a noisy one, but they use teacher forcing.
Teacher forcing, meaning it gets the correct previous frame as input during training.
Correct. It sees the ground truth past frame from the dataset to predict the next frame. This step mainly just gets the model's architecture used to the causal input structure and the next frame prediction task, still within a diffusion-like objective.
Okay, so stage 1 adapts the architecture using perfect inputs. What's stage 2?
Stage 2 is consistency distillation. This is more of an initialization step, something often done before adversarial training to help things converge faster. It's compatible with their setup. Interestingly, they mentioned they deliberately omitted using Classifier-Free Guidance, CFG, here and in the next stage.
Oh, CFG is usually pretty important for guiding diffusion models, isn't it?
It is for steering generation strongly towards a prompt, but they found that in their specific autoregressive single-step setup, CFG actually introduced visual artifacts. So they decided to skip it for better stability and cleaner output.
Interesting trade-off. Sacrificing some prompt adherence for stability. Okay, so that leads to stage 3, the adversarial part. The one you said build on previous APT work, but add something new.
Exactly. Stage 3 is adversarial training. This is where the magic really happens for getting robust, long-duration generation and where that student forcing comes in.
Okay, tell me about the adversarial setup, generator versus discriminator.
Right. So they train a discriminator model alongside the generator. Cleverly, this discriminator uses the same causal architecture as the generator and is even initialized with the generator's weights from stage 1. Its job isn't to predict the next frame, but to judge. Is this video clip real or fake?
Judging realism. How does it do that?
Another smart design choice. Instead of giving one score for the whole clip, the discriminator outputs a real fake score for every single frame in the input sequence. This allows for what they call parallel, multi-duration discrimination. It can effectively assess realism across different timescales within the clip.
Okay, frame-by-frame realism checks. Now, how does this connect to student forcing? You said that was critical.
This is probably the most crucial part for making long generation work, and Figure 7 in the paper shows it dramatically. If you only train using teacher forcing, stage 1 style, the model always sees perfect pass frames during training.
But at inference time, it doesn't have that perfect data.
Exactly. At inference, it has to use its own output from the previous step as input for the current step. Any tiny error it makes gets fed back in. Without training to handle these slightly imperfect self-generated inputs, the errors just compound catastrophically. Figure 7 shows the teacher-forced model basically falling apart, generating garbage after just a few seconds.
The classic compounding error problem in autoregressive models. It bites hard.
It does. So student forcing directly attacks this. During this adversarial training stage, the generator is trained using the actual frame it generated in the previous step as the input for the current step.
So it learns to cope with its own imperfections.
Precisely. It learns to be robust to those small errors, preventing them from snowballing. It's like learning to ride a bike you learn by trying, wobbling, correcting, not just by watching someone else ride perfectly.
That makes intuitive sense. A subtle but important detail you mentioned.
Yeah, for stability during training, they actually detach the gradient flow from the pass frame input itself. But importantly, they do allow gradients to flow back through the KV cache. This lets the model learn the sequential dependencies without making the training unstable.
Okay, that's a clever training technique. What about the specific loss function for the Jan part?
They used the R3 Jan objective. It incorporates relativistic loss and some regularizations, R1, R2. They found this specific Jan loss setup was more stable for training these long sequences compared to maybe simpler alternatives like the non-saturating loss. Stability is gold when you're pushing the boundaries like this.
Makes sense. And one more training puzzle. Generating long videos. You said they generate up to a minute. Standard video data sets often have shorter clips. How do you train for a minute if your data isn't a minute long?
Yeah, that's another really neat trick in their training strategy. They don't actually need minute-long ground truth videos. Here's how it works. The generator is trained to be capable of outputting a long sequence, say 60 seconds worth of latent frames.
Okay, the generator can make long videos.
Right. But the discriminator doesn't look at that whole 60-second generated video at once. That would likely be too memory intensive. Instead, they chop up the long generated video into shorter segments, maybe 10 seconds long.
And the discriminator judges these shorter segments.
Exactly. It judges the 10-second generated segments against 10-second segments from real videos. And to help the generator learn smooth transitions between segments, these 10-second chunks have a small overlap, maybe 1 second.
Okay. So the discriminator only needs to tell if a 10-second clip looks real or fake. It doesn't need the correct 60-second answer.
Precisely. This lets them train the generator to maintain coherence over that full 60 seconds, even though the discriminator is only ever looking at shorter pieces. It's a smart way to leverage the adversarial setup to work around data limitations for long sequences. Figure 3rd versus 3E really drives this home. Without this long video training strategy, the models just break down on longer generations.
That's really clever. Using the discriminator's local view to enforce global coherence in the generator. Did they mention how they managed the memory for the generator during this long segment training?
Yes, even generating the 60-second sequence in the generator can be demanding. So during training, they also generate it segment by segment, reusing the KV cache from the end of one segment to start the next. But similar to the student forcing input, they detach the gradients across these segment boundaries.
Okay, process chunk by chunk, pass the state, but don't backpropagate across the chunk boundary.
Right. They accumulate the loss after each segment and then backpropagate. It definitely makes the training slower than just training on short clips directly, but they argue it's essential for learning those crucial long-range dependencies needed for minute-long videos.
Okay, we've got the architecture, the training. Quite a journey. Let's get to the payoff, the results. You teased them earlier, 24 VPs.
Yeah, let's look at Table 4. The performance numbers are really the headline here. Their 8B parameter model hits 24.8 frames per second at that 736 by 416 resolution on a single H100.
That's properly real time. And the latency.
Just 0.16 seconds. Super responsive.
And how does that stack up against prior work? You mentioned CosVid.
Right. They compare against CosVid, a 5B model. CosVid managed about 9.4 FPs with a much higher latency of 1.30 seconds, and that was at a lower resolution too, 640 by 352. So APT is significantly faster and more responsive.
That's a huge difference. What about higher resolutions?
They show that on 8 H100s, they can hit 24.2 FPs at 1280 by 720, still with very low latency. 0.1 sems, so it scales pretty well.
And the duration hitting a full minute, 1440 frames, that feels like a qualitative leap too.
It really is. Being able to stream generation continuously for a minute using the KV cache without stopping and reprocessing is a big deal. Previous one-step methods they compared against, like the original APT, chopped out around 49 frames. Going to 1440 frames unlocks much richer, longer interactive possibilities. Figures 3 and 4 show some examples of these longer videos.
Speed and duration are crucial for interaction. What about the visual quality? Does it hold up? Table 1 has some benchmarks.
Quality seems quite competitive. They use VBench I2V, which tests text-to-video generation. On shorter 120-frame clips, AAPT actually scores better than their diffusion baseline on frame quality and image conditioning adherence.
So the adversarial training might even be improving perceived quality.
It often does, yeah. GNNs can sometimes produce sharper results. Now, on the really challenging 1440-frame, minute-long test, AAPT gets the best overall quality score among the compared methods. This really shows its strength in maintaining coherence over time.
Any downsides on quality?
They do note a slight dip in temporal quality scores compared to the diffusion baseline, but it's still strong overall. They also suggest some competitors' high temporal scores might be linked to quirks in their training data, like using a lower frame rate videos.
Okay, so overall, very competitive quality, especially on long sequences. And they showed specific interactive demos too, right? Pose control, camera control.
Yes, figures 5 and 6, and tables 2 and 3 cover these. These demos are where you really see the real-time aspect payoff. Figure 5 shows controlling a virtual human using pose skeletons, like a digital puppet.
How did it do there?
Table 2 shows it achieves really good pose accuracy, second only to a state-of-the-art model specifically built for human generation, OmniHuman 1, while keeping good visual quality. Then Figure 6 and Table 3 show camera-controlled world exploration, basically flying a camera through a generated scene in real time.
And the performance there?
They actually set a new state-of-the-art on several metrics for that task, including FVD, freshette video distance, which measures realism and diversity and also appearance consistency. These demos really hammer home that the model can take user input on the fly and generate the corresponding video response almost instantly.
So pulling this all together, this feels like more than just an incremental speed up. It feels like a genuinely significant step towards making those interactive AI applications feasible. Real-time, high-res, minute-long interaction.
I think that's fair to say. It feels quite transformative for the potential of generative video. Taking these powerful but slow models and giving them real-time capabilities for reasonably long durations is a big achievement.
And the Oblation Studies they did really back up their design choices, right?
Absolutely. Table 5 and Figure 3 clearly show that the long video training strategy is non-negotiable. Without it, the models just can't handle generating coherent video past a few seconds.
And Figure 7, that comparison between student forcing and teacher forcing is just brutal.
It really is. Seeing how quickly the teacher-forced model collapses into noise just makes the case for student forcing so powerfully. It seems absolutely essential for preventing that error accumulation during inference. It's the difference between a few seconds and a full minute of stable generation.
But like all research, it's not the final destination.
Yeah.
What limitations did they acknowledge? Where's the room for improvement?
They were pretty clear about the remaining challenges. One is consistency over very long durations. Keeping every detail of a character or scene perfectly stable for many minutes is still really hard.
Even with all their techniques.
Yeah. They think it's partly the generator's sliding window, which has a limited direct view, and maybe partly the discriminator not quite capturing ultra-long-range temporal patterns perfectly, even with the segment training.
So perfect minute-plus consistency is still the next frontier.
Seems like it. They also mentioned training speed, that complex long video training is slow. And another interesting point, because it's one-step generation, if a visual glitch does appear in one frame, the model's own temporal consistency mechanism might actually cause that glitch to persist for a little while, kind of getting stuck in the video.
The consistency works against you sometimes if there's a momentary error.
Exactly. And finally, while it's great up to a minute, they noted that trying to generate significantly longer, like 5 minutes, zero shot without specific further training can lead to artifacts, so extending that stable duration even further is ongoing work.
Makes sense. It's a huge leap, but the quest for perfect, endless, coherent video continues. Okay, so to wrap up, AAPT is this really innovative method taking latent diffusion models and making them fast, real-time autoregressive generators. Key ingredients are architectural changes, smart use of KV cache with a sliding window, and this critical adversarial post-training using student forcing and a special long video training approach.
And the result is minute long video generation at real-time speeds, enabling genuine interactive applications with impressive performance.
Which really does open up exciting possibilities, but it also raises a big question for the future, doesn't it?
It does. As we keep pushing for faster, longer, more efficient interactive generation, how do we make sure we also maintain or even improve that really complex consistency of characters, objects, scene logic over these much longer timescales?
Yeah, how do you balance the speed and duration with the need for everything to stay perfectly coherent?
It feels like maybe the next step involves getting discriminators, or maybe entirely new mechanisms that can understand and enforce much more sophisticated, much longer-range temporal relationships than we can currently manage.
That challenge of long-range consistency definitely feels like the next major hurdle. Still, the idea of truly dynamic, real-time generative worlds feels substantially closer after understanding this work. Thanks for walking us through this paper.
My pleasure. It's fascinating stuff.